Now that we know how to find the values of double integrals over general regions, and general regions mean that rather than just rectangles on the xy plane, we now have the tools, the tape measure method gives us a tool to describe a general region in the xy plane. But there is more than one way to do that, right? When we did the previous example, we ended up making the choice of describing the region of integration as being bounded on the bottom by some function, the graph of some function of x, and on the top by the graph of some function of x. But that's not the only choice we could have made. We could have chosen to start the process by looking at horizontal cross-sections instead of vertical, by bounding the left side of our region by the graph of some function of y, x equals a function of y, and then bounding the right-hand side by x equals some other function of y, and doing that slice first, and then projecting that onto the y-axis and getting constant bounds for y instead. So those two different methods of describing a two-dimensional region are respectively called a type 1 method and a type 2 method by some calculus textbook authors that feel like they need to give terminology for every little thing. And so sometimes it turns out that one of those approaches is either easier than the other because it gives us nicer looking functions and expressions to participate in our limits of integration, or sometimes, as the last activity in this chapter, which I encourage you to look at on your own time, shows, sometimes an integral is impossible to do because an antiderivative is impossible to do in one of those directions, but the antiderivative becomes possible if we choose the other, the type 2 versus type 1, or vice versa, way of describing the region. So the goal of this last activity is to get us some practice with doing both, right? Taking a region of integration in the xy plane, describing it as a type 1 region and setting up an iterated integral over it, and then re-measuring it, re-tape measuring it by slicing it the other direction as a type 2 region, and then set up an iterated integral in that direction instead. So in this example, we're asked to consider the double integral 4 minus x minus 2y over the triangular region whose vertices are at the origin, at 4, 0, and at 0, 2. So I think our first goal here is going to be to figure out how to describe that region. We know that if the vertices, let's just write the vertices out here, 0, 0, 4, 0, and 0, 2. Right? So there's my three vertices of this triangle. Evidently, two of the sides of this triangle are going to be right on the x and y axis, respectively. So one side is going to be y equals 0, that's the x-axis, and x is going to range from 0 to 4. And the vertical side along the y-axis is going to just be the y-axis, x equals 0, y ranging from 0 to 2. So there's those sides, and of course the interesting side is the diagonal side. And so to find an equation for that diagonal side, let's do it by, well, we would just have to find a point-slope equation for the line that passes through the point 0, 2 and 4, 0. Or slope-intercept, however you like it. If we do slope-intercept, we can find the slope is -1/2. So y equals -1/2 x plus 2. Gives me an equation of the line that passes through that pair of points. And then I'm again going to let x range from 0 to 4. And that gives me an equation for the top side. So the fact that we wrote down an equation for this top side, which cast y as a function of x, gives us kind of the most natural entry point into describing this as a type 1 region, right? Where we bound y in between a pair of functions of x, and then we let x range between constant bounds. So my functions were on the bottom, f of x equals 0, and on the top, g of x is -1/2 times x plus 2. And then I want to let x range from 0 to 4. So I'll take this limit of integration all the way out to here. So here is then that description of this region of integration, again in a type 1 fashion, because we're taking vertical cross sections. The bottom limit is y equals 0. The top limit is y equals -1/2 x plus 2. When we reverse the limits of integration on a double integral, an iterated double integral, we always have to go back to the drawing board and re-tape measure that region. So if we started out with an iterated integral that was with respect to y first and then x, so the dy dx version, the type 1 description, It's not as simple as just sort of switching the x and the y around in those limits of integration and getting the other way correct. We have to go all the way back to the original picture. And instead of a vertical tape measure, take out a horizontal tape measure. Find a function of y that bounds the left side and the right side of the region. So in this case, that was the function 0 and negative 2y plus 4. And then with that redescription, squish that onto the y-axis, find the constant bounds for y. And so the new integral that we get looks pretty different than the old integral. The integrands are the same, but the limits of integration are quite different. And so the last activity that I'd like for you to at least get started on, and if you have to run because it's 1:15, feel free to do so, but I'll hang out if you want to work on this activity together, just gives us another example to work with where we're given a region which is first of all being described in a type 1 fashion. We range from y equals x to y equals square root of x, and x ranges from 0 to 1. And so your goal in this activity is going to be to set up the opposite, set up the reverse integral. How would this integral look if we wanted to do it with respect to x first and then y? And ultimately, the answers that we get, right, the ultimate value of these integrals should not depend on which way we describe it, type 1 or type 2. But being able to convert in between those two can sometimes take a messy integral into a slightly tidier integral. Sometimes it can take an impossible integral and render it possible. So let's use this as the example that we'll finish up with today. So our last example of reversing the order of integration for today. The setup is really everything. I'm going to trust that you can do the actual evaluation of the integral as an iterated integral. That's just sort of repeated application of single variable calculus. So the big new skill for today is that tape measuring method. Sorry about that. The big skill for today is reversing the order of integration, right? Taking a type 1 region, redescribing it as type 2 using what I call the tape measure method. And so this last example asks us to do that with this type 1 integral that starts with the bounds y ranging from x to the square root of x and x ranging from 0 to 1. So what they ask us to do, and this is always a good idea, and you can use this Desmos worksheet to help you with that, is to sketch out the region that you're trying to integrate over. Just to get started. And then our task is going to be to redescribe that region as a type 2 instead of a type 1 region. So if we first start by sketching this region out, we sketch the curve y equals x, diagonal line. We sketch the curve y equals the square root of x. It's a half a parabola on its side, right? And then we look at the region in between those two curves, between x equals 0 and x equals 1, and we get a region that looks like this. Right? So there's y equals x on the bottom, y equals square root of x on the top, and when I squish that region onto the x-axis, it covers the portion of the x-axis from x equals 0 to x equals 1. So to turn this around into a type 2, you had to turn both of these equations around into making x the subject instead of y. And then think about the leftmost and the rightmost extent of this region. So when I turn y equals x around, so that x is solved for, well, that's the easiest thing in the world to do. Just turn the equation backwards. X is equal to y. If y is equal to x, then x must be equal to y. So that's my right-hand limit function for this region. My left-hand limit function will be what I get if I turn y equals square root of x into making x the subject. And so I square both sides and find out x should be equal to y squared. So as a type 2 region, x ranges from y squared on the left side to y on the right side. And then when I squish that region onto the y-axis, it covers the portion of the y-axis from y equals 0 to y equals 1. So sure enough, the nice thing about this tool, right, is we can put both of these on top of one another and make sure that they're exactly the same. And indeed, that is the case here. So anytime you have to reverse the limits of integration, having a picture, a visual like this one, is always a good idea to make sure that after you've done the work, you're still describing the same region as when we started, because the answer of your integral, the value of the double integral, should not depend on which way we decided to slice up the domain to create an iterated integral in the process.